Three.
And welcome everybody to this part 5 of the practical workshops on the identification of rock-forming minerals in hand specimen. For this session, we're looking at some of the metamorphic minerals, or the more common metamorphic minerals. So we'll start off, we'll do a recap from last time so that we know exactly where we are. And then we'll go into some of these metamorphic minerals. Remember, I'm not covering the whole gamut of minerals, just a few of them. So if you can mute your systems and switch everything off, that will be fine. Right, last time, well, really, this is several times. Whereabouts have we got to? Well, we looked at things like olivine and quartz. The characteristic things about olivine and quartz, they tended to be anhedral, so not really any good crystal shape, granular, but they had a glassy appearance. So that was a useful clue to the identification of things like that. We looked at plagioclase, and we recognized these euhedral, so it's good crystal shape, but these lath-shaped crystals tend to be translucent. I remember the thing we said with plagioclase related to color. There's not much you can say about the feldspars generally, but the one thing you can say is plagioclase is never pink. So if you've got something pink, it's not plagioclase. So we looked at alkali feldspars. They tended to be more opaque and more satiny luster, but they were still lath-shaped, generally euhedral crystals. We then looked at some of the micas, and we recognized those as being very glossy luster, almost a plastic luster, and they occurred as little flecks and flakes. If we had a lot of material there, then we had what we call books, like a pile of leaves or a pile of sheets of mica plates. And we looked at the pyroxenes and recognized that, generally speaking, pyroxenes, we often had good crystals, that they were quite stumpy. They were prismatic, but stumpy, and tended to be rather dark, black, brown, although we could have green as well. And then we looked at the amphiboles, and the thing that characterized the amphiboles generally was the bladed, needle-like almost crystal habit of the amphiboles that tended to be quite dark, but very glossy. And if you remember, we talked about having both pyroxene and amphibole together. And I said that we tend to find that if you have the two together, the amphibole tends to be more lustrous, has more of a glossy luster than the pyroxene. So if you've got the two together, that can be one way to distinguish between the two. And of course, you'd also look for the bladed euhedral acicular crystal form for the amphiboles. And then we looked at some more possibly less common minerals, granular, colorless, rather like quartz, but a very greasy appearance would lead us to the identification of nepheline, which, if you remember, was one of these almost feldspars. It just didn't have enough quartz to be a feldspar, and it was something that we called a feldspathoid, or in the modern parlance, the foids, not a name I like myself, but that's what they call them now. We also looked at, remember, pseudoleucite. It was originally leucite, but pseudomorphs after original leucite, which had started to decompose and break down. And we just had general white spots. But when we looked at the white spots, they're actually composed of both nepheline and alkali feldspar. So that was one way to tell that you had originally leucite that had started to break down to pseudo-leucite. We looked at analcite, which tended to be just white spots, sometimes somewhat subhedral, vitreous luster, light coloured, and often associated with the more volcanic mafic rocks. Finally, we looked at tourmaline with these characteristic elongated prismatic crystals, black to dark brown. But one great ID tool is this three-sided section with these beveled edges. So that allowed us to identify the presence of tourmaline. And tourmaline would be associated, generally speaking, with the micas or quartz or both together. So that's where we got to at the end of the last 4 sessions. Actually, that's a summary of the last 4. So let's move on. Well, I wonder how many people can remember this. White spots. And if we look at some of these white spots, there's a white spot with a middle to it, and there's some nepheline, and there's some alkali feldspar. However, we're not looking at this bit tonight. We've done those. I want to concentrate on these little black bits. These black bits, all the ones that I'm pointing out. These little black bits there. Don't really see much of a crystal shape. They look sort of rounded. I'm just identifying some bits up there as well. So black rounded, almost rounded bits there. Nothing much more we can say about that. There's your scale bar, just to let you know whereabouts size-wise we are. And, well, you might remember this one, this greasy anhedral material. Well, that's nepheline. But we're not bothering with the nepheline because we've done that. It is these little black bits here, that one there, and that one up there. And there's quite a nice little one there. Sort of round. This has almost got a bit of a subhedral habit to it. That one there has as well, and that one there. Almost like sort of octahedra. There's another bit there and a little bit there. So quite a few black bits which are either rounded or almost octahedral. And scale bar for your to know where you are. This is another one that we've seen before, and we looked at these bladed dark green acicular crystals and identified those as an amphibole, but it's these things. Rounded black. There's a bit there, it's hidden, it's a bit underneath, there's a bit of alkali feldspar that's covering this bit. But now we get the opportunity to look at this black in a little bit more detail. Almost an octahedral shape out of that. It's quite glossy. Can't see any cleavage. That's glossy as well, that piece up there. So can't really tell much more about that, but no real noticeable cleavage, but this glossy, quite glossy luster, and this black color and this shape. Oh, there's another piece down there, slightly out of focus, that bit down there. And that's a piece of quite a large crystal. Again, these crystals here are quite large because there's a 1 centimeter scale bar there. So these are quite large crystals. And, well, they, as it says there, these are garnets. And the characteristics of garnets, well, this octahedra, now I've got octahedral in inverted commas because they're not actually octahedra, they're dodecahedra. But if you can spot the difference between dodecahedra and octahedra in an specimen, then you've got almost perfect crystals. Generally speaking, you can't. So that's why I call them octahedral. But if the crystal hasn't formed particularly well, then they look, well, they just look rounded. So that's why I've got that rounded term there. And as I say, often subhedral, where you might find some crystal edges on these rounded, almost octahedral crystals. Now, if you get quite thin sections of this material, it's transparent. But if it's massive, as in that last slide, it becomes opaque. You can't see through it. And so it's opaque if it's massive or if it's dark. And those, the ones we looked at, the last 3 slides, those were this dark variety. We mentioned the vitreous glassy luster, and that's a characteristic of this particular, well, it's a characteristic of the garnets generally. Now, this particular garnet you will often associate with metamorphic rocks. And indeed, I'll be talking a little bit more about the significance of metamorphic garnet in a moment. But the last 3 rocks that we've looked at have all been igneous rocks. And you do get garnet in igneous rocks as primary garnet. And that's what we've been looking at. We've been looking at this variety called melanite, which is a calcium, mainly calcium. There might be a bit of iron in the structure, but there's also titanium. So it's a calcium titanium with or without a bit of iron in the structure as well. And as I say, that's called melanite, which means black. And it occurs particularly in alkaline rocks. And all those rocks that we've just been looking at are alkaline, and they are all also silica undersaturated. So those are alkali cyanites. And melanite garnet is a common component in those alkali cyanites. The other thing that we mentioned when we looked at the pictures, there's no cleavage in the garnets. So if you've got the felspathoids, and you can have, as you saw previously, you saw the amphiboles. If you've got felspathoids, you've got amphiboles, you can have alkali feldspars. You can always look out for these black garnets, the melanite garnet, because that's quite a possible occurrence there as well. So that's igneous garnet. And yes, I did lie about the title. I said we were going to do metamorphic rocks, but since we're doing garnets, I had to include the non-metamorphic garnets first. So we're now going to get back on course and look at the more metamorphic varieties, although that's possibly questionable, as you'll see in a moment. Let's just put that detail for garnet, for the melanite, into what has become our standard way of recording these things. So the crystal habit is, well, remember, it's not octahedral, it's actually dodecahedral. Euhedral rounded is one of the common forms. Tends to be transparent, but when it's massive or black, then it's opaque. The glassy vitreous nature, no cleavage. For melanite, it's black, and there's no twins there. So that's the igneous garnet. Now, let's go on to this one. First of all, there's our scale bar down there, 1 centimeter, and it's this thing here, that thing there, that lump there, that one there, and that one there, and that one sort of round there. And so these are big. And again, these are garnets. These are fractures. These aren't cleavage planes. These are fractures on there. They're not as regular as you would expect cleavage planes to be. They're a bit irregular. So these are fractures. But this is a pinkish red variety of garnet. And as I say, these are 2 to 3 centimeter size garnets, so quite large garnets. And these garnets occur within this ground mass, which is made up of clinopyroxene, which is this dark stuff, and orthopyroxene, probably enstatite, which is this white material. So the ground mass is a combination of clinopyroxene and orthopyroxene, but because the crystals are very small, it's quite difficult to be able to identify each of these separately. There's a bigger piece here, which you might possibly be able to think that's a bit of cleavage on this bit of pyroxene, possibly that's cleavage. But anyway, we're not looking at the pyroxenes. We've done the pyroxenes. It's these garnets that we are looking at now. Glassy luster, quite shiny, gives you a hint of transparency with this piece, and probably that little fragment there is somewhat transparent as well. These pieces here, of course, if you've got dark minerals behind, then you're not going to notice the transparency so easily. So that's something to bear in mind. Pink color, pinky red, as I said, good glossy luster, but again, this rounded appearance. That one's rounded, that one there, possibly a hint of some crystal edges there, sort of rounded there. It's got bits of pyroxene in front of it as well. This one here is almost subhedral, and there's probably a bit of an edge down there. This is probably a subhedral piece there, quite a nice crystal shape. And this one, yeah, getting towards subhedral, octahedral, dodecahedral shape there. Now, I said that I was talking about metamorphic rocks. Well, debatable whether this is a metamorphic rock or not. One of the characteristics of metamorphic rocks, which we'll see in a moment, is having a response to strain, particularly, well, for regional metamorphic rocks, that is. Now, this doesn't have any indication of strain within the texture in this ground mass here. So you might be forgiven for thinking that this wasn't metamorphic. And I say it is questionable where you want to classify this. This is a piece of the mantle, and it's a part of the mantle where we're in the stability field for garnet, and so garnet is quite happy to exist in here. It's also in this stability field where we have these two pyroxenes, which are also stable, but because there's no real structure, strain-related structure, texture within this ground mass, you may or may not wish to call it metamorphic. It is, as I say, it is part of the mantle, and it will have been from at least 120 kilometers depth, probably more. But as I say, it doesn't show the classic textures that you would expect. One interesting thing about the garnets is that during metamorphism, during proper metamorphism, these things grow, and if you have a strain in the rock within which the garnets are growing, the garnets actually rotate. And what you can often find if you look very closely with a microscope, take sections, and if you've got inclusions, garnets tend to have quite a lot of inclusions. What you can actually find is that the trails of inclusions actually show this rotation, and you can get indications of the amount of strain and the directions of strain by studying the rotation of these garnets and looking at the how the inclusions have varied. So these are quite useful things. I'll say a little bit more about these the value of garnets in a moment when we look at a few more of the metamorphic rocks. So, as I say, you might or might not want to call that metamorphic. Right, I'm not dealing with these common metamorphic minerals because we've already done these. We've done micas. Micas are a common metamorphic mineral, particularly in regional metamorphic rocks. And we get both the muscovite or the white mica and the dark, the biotite type micas. within metamorphic rocks. Alkali feldspars are also very common in metamorphic rocks, as is quartz and amphibole as well. So these will be a standard inventory for many of the metamorphic rocks. Say we've done these previously, so I'm not going to consider those tonight. It's only the ones that we've not seen before that we'll consider. There's a typical metamorphic rock. There's your scale bar. That's a centimetre scale along there. And all these are plates, flakes of white mica glistening in the light. And that, you would call that a mica schist. That's a typical schist-like metamorphic rock. And the plates of mica are growing along the orientation of the strain that's being applied to these rocks. So that's a classic mica schist, standard metamorphic, medium grade metamorphic rock. If we apply more heating and more strain to a schist, we go up into the higher grade metamorphic rocks, which are the gneisses. And so those are really high grade. And so this is sort of an intermediate grade of metamorphic rock. Now let's look at this again. We've got a schistosity. That's this orientation of sheets of mica, and this you would call a mica schist. But it's these little bits that are arrowed that I want to concentrate on. There. There's one there I've just spotted. There. There's a bit there. The more you look at this, another one there, another one there. The more you look at this, well, there's one there. There's one. The more you look at this, you recognise that these little rounded pink things tend to be quite abundant in this rock. And you've seen this rock previously when we talked about micas. So we've done that one. Quite small in this one. You see that there's the scale bar there. That's 1 centimetre. So these 2 or 3 millimetre sized little round bits. We've got some better ones there, slightly bigger, but this pinkish colour, pinky brown, pinky red colour to these bits here, dotted all over the place. And within our generally schistose arrangement of micas, there's micas dotted about there, lots of micas there. But these pink, almost rounded grains, almost octahedral, this is garnet. This is a pinky red variety of garnet. And you would call this particular rock type, because there's so much garnet there, this is a garnet mica schist. Another bit of garnet up there. This is a garnet mica schist as well. So nice big garnets in there. And if we want to go up a scale, that's our 2 centimetre scale bar there. So some even bigger garnets in this piece, with some nice pyroxene dotted about there. But again, as I say, we're not looking at pyroxene because we've done that. But this is almost euhedral. You can begin to see some edges appearing or surviving, better way of putting it, surviving on this piece of garnet. But pinky red colour, pinky red there, quite transparent. That piece there, almost see through it. That piece there, you can almost see through it. So this is again another metamorphic rock of a higher grade this time. And the presence of garnet is important. I said I was going to talk a little bit more about garnet. Garnet is important because garnet is produced as a response to pressure. We saw in that piece of the mantle that I showed you just now, that we were in the garnet stability field. And garnet is stable under these high pressure conditions. And we use garnet, or the presence of garnet in metamorphic rocks, as a pressure indicator. It tells us something about the metamorphic grade, the metamorphic facies. And whenever we see garnet, we recognize that it is quite a high grade, well, it's a very high grade of metamorphic rock. So the garnet is an index mineral. We call it an index mineral, and it's an index mineral for pressure, and it's high pressure. And we, as I say, we're commonly 90 to 120 kilometers depth into the mantle. But in terms of identifying the mineral, pinkish color, this one's almost euhedral, subhedral to euhedral, glossy, transparent, almost transparent, glossy. Those are the characteristics of that garnet. And this garnet, as the text there says, this is what we call, this is the pyrope garnet, and it's the magnesium garnet. And you'll remember that I talked about magnesium and what magnesium can tell us previously in an earlier one of these talks. Magnesium is related to depth within the mantle, and many magnesium-rich minerals have an origin deep within the mantle, and the pyrope garnet is no exception to that. So it's the mantle stable variety, and it's high pressure index mineral, indicator mineral. We've already mentioned this inverted commas octahedral, but you will now know it as dodecahedral in reality, because that's its crystal system. It fits into that shape. Rounded if it's not properly formed crystals. Transparent to opaque, but again, if we've got a lot of it and there's darker material behind it, then it tends to appear a little bit more opaque. The vitreous glassy luster is characteristic, and for the pyrope garnets, this pink to red color is characteristic of the pyrope garnets. And as I've said before, there is no cleavage with garnets. So we put that into our standard form now. There's again, remember, dodecahedral, but we call it octahedral and rounded. Transparent, but when it's massive, it's opaque. It's glassy vitreous luster, pink or red color, and there's no cleavage and there's no twinning. So remember, garnets are important because they are an index mineral for pressure. Right, let's move on to something else. First of all, let's look at our scale bar. There's our scale bar there, 1 centimeter. And these lath-shaped blue, pretty blue crystals, 2 there, there's 1 there. There's a nice bladed one there, there's 1 there. There's 1 there, there's 1 there. And the more you look, the more you see them all over the place. Lots and lots of these pretty blue bladed crystals. We come back to this one, you can possibly just about pick out some cleavage, longitudinal cleavage, long axis cleavage on this piece, and possibly a bit in there, possibly a bit in there, some on that one, little bit in there, little bit in there, possibly in there. The other things you will notice, since we've just talked about these, are the pyrope garnets dotted about down there and down there and down there. In fact, there's lots of them. So that will tell you that this is a high pressure metamorphic rock we're looking at, and this overall blue color and these lath-shaped crystals with this longitudinal long axis cleavage, these are the characteristics of kyanite. So this is kyanite, which is an aluminosilicate, and this classic blue color for kyanite. As I say, it's all over the place here, dotted about. There's that nice little bit of darker garnet. This little bit of garnet here is interesting. It's actually got some chromium in it, which is why it's a darker red. So it's a chromium-rich pyrope garnet. So this, as I say, this is blue kyanite. So let's look at the characteristics of kyanite. Bladed prismatic crystals, as I mentioned, generally transparent to translucent. It can be completely transparent. This vitreous glassy luster, and it's often got this characteristic blue color, but it can be sometimes colorless or even white. And it has this longitudinal cleavage. It is twin, but they're not always visible, not always apparent, but it does have twins. So that's kyanite. That's another one of these high pressure metamorphic minerals. And as I say, this is one of the aluminosilicate minerals. So we put that one into its standard form. There we go. The bladed prismatic elongate crystals, transparent or translucent, vitreous luster with this longitudinal cleavage. And that blue color, characteristic blue color, is, I think, the giveaway for this kyanite. And in fact, when it's completely transparent and a deep blue, it's a semi-precious stone. So quite an attractive stone. But another high pressure mineral. Right, and here's another. Well, you'll be able to identify these pinky round bits, pinky red rounded bits now, because you're certainly getting your fill of pyrope garnet. So you can recognize that this is also a high pressure rock because of the garnets in there. There's also a little bit of foliation beginning to develop. You see, we've got some planar structure, planar texture along there. There's also on this edge, you've got planar texture along there. But it's this mineral here, possibly hints of cleavage on there, characteristic green color. Does tend to be a little bit more granular as here. All this material here is granular. This stuff here is definitely granular. And that stuff there is granular, but it's that characteristic green color which gives it away. And it's a green color in association with the red garnet. This, with its cleavage, is another pyroxene. This is the sodium-rich pyroxene omphacite. Now, this is omphacite pyroxene, and this classic greenish color is the giveaway for this mineral. And as I say, find my pointer. There's possibly some hint of cleavage within there, but often you get this more granular appearance to the omphacite. But again, omphacite, this sodium-rich pyroxene, this omphacite, is a high-pressure mineral, and it is a high-pressure. It is the highest pressure assemblage here, where we've got garnet on omphacite. Where's my pointer there? Garnet and omphacite, and we are now up in the eclogite fasces. In fact, this is a piece of eclogite. This is eclogite fasces metamorphic rock. So this is deep burial, 120 kilometers, that sort of depth within the Earth's mantle. But like I say, it's the association with the garnet, this bright green color, which is the giveaway for this omphacite pyroxene. So let's look at the words for this. It's often anhedral, but it can be subhedral, as that piece was there that we've just looked at. Translucent sometimes, but it can be transparent, particularly if you've got thin enough pieces of it, it'll be transparent. A very vitreous to silky luster, so slightly down a notch from the very glassy materials that we've been looking at previously, but nonetheless still quite quite glossy. It's got a longitudinal cleavage. If you happen to have a basal section, as in all pyroxenes, it's a 90-degree to intersecting cleavages at 90 degrees on basal sections, if you're lucky enough to have basal sections. But it's this bright green, which is the giveaway for that omphacite. However, omphacite can also be colorless, and in which case you'd make the ID purely by association of garnet, maybe kyanite with it as well. So you'd need to have something else, or of course you'd do a thin section and check it out under thin section, where you'd be able to ID it properly. But since we're talking hand specimens, remember we can't always get to a complete ID using hand specimen identification, so have to bear that in mind. So we put omphacite. Oh yes, remember omphacite is a clinopyroxene. It's one of the clinopyroxenes. So should have prismatic crystals, but it's often anhedral. It's granular form, transparent, translucent, glassy, vitreous, but it merging towards silky. So a slight notch down on the purely glassy. Longitudinal cleavage if you've got stumpy crystals, or 90-degree intersecting cleavages if you've got a basal section. And it's that green color which is the giveaway for most of the omphacite. No twins, but you'd look at the associations with that with the omphacite. If you think you've got omphacite and you've got garnet there, then you probably are talking about omphacite. Right, where are we? Okay, what have we learned? Hopefully, you've had plenty of opportunity now to identify garnet, both in the igneous form. Remember, you do that by association as well as the color black, but it's that octahedral to subhedral rounded crystal habit. The vitreous glassy luster would be another substantiator for garnet. Kyanite, well, that blue, classic blue color with the bladed elongate crystals, that longitudinal cleavage. If you happen to have white kyanite, then it's a little bit more difficult to ID completely, and you'd need to do thin sections. So that would be a bit more difficult in hand specimen. You'd look at the associations as well and see what was there. And the omphacite, again, subhedral possibly, but you may have a little bit more, slightly more crystal habit, good crystal shape in places, but it's that characteristic green color again that is the giveaway, and the association. Right, that concludes looking at a range of minerals over the last 5 weeks. We've looked at a range of relatively common minerals. Now, you get a hand specimen, you look at it, the two most obvious things that leap out at you, and here we're talking about either igneous or metamorphic rocks, and as long as you've got, as long as it's coarse enough grained to be able to see the crystals, the two most obvious things are the shape of the crystals and the color. I know I said right at the start of this lecture series that color wasn't a good ID for a range of minerals, but it can give you a lead in to other things, and that's the importance about color. So what you'd do, you'd grab your hand specimen, preferably of a reasonable size, so you can see a range of features, and you'd look for any crystals that leap out at you with a particular shape, and is there any particular color that you notice. So you'd then, having sort of picked out those either the crystal shapes or the colors, and use all the characteristics that we've listed previously, we would use those properties that we can identify and the properties that we listed to begin to get some idea about what mineral you're actually looking at. And then you'd confirm by looking at the other properties that we've been talking about over the weeks. It'd also corroborate that by these associations. Remember, we talked quite a bit about associations, so let's just look at recap on what we talked about with these associations. For example, we said that it was highly unlikely that you'd get olivine and quartz together in a rock because olivine plus quartz react to give you pyroxene. It's that sort of issue. And the only situation where you are possibly likely to have some quartz is if the quartz got in not as a primary constituent of the magma. And I'm thinking lamprifiers here, where it is conceivable that you would have an olivine-rich lamprifier, no problem with that, that has begun to assimilate a bit of crust as it's been emplaced, and possibly some quartz has been entrained within the consolidating magma as it's risen up through the crust. So that's the situation where you could get some quartz within your olivine-rich, olivine-bearing igneous rock. But you'd find the quartz would be unhappy and it would be showing reaction rims and so forth. The other unlikely association is quartz with nepheline, because remember, nepheline is a felspathoid. It occurs in silica undersaturated, that means silica poor rocks. And so if you've got quartz in the rock, it will have combined with the nepheline to make feldspar. So quartz and nepheline is again highly unlikely. We talked about the question of quartz with only plagioclase. Very rare would you find quartz with only plagioclase. Rare unless you're working on the research section that I'm looking at in Cyprus, where all you get is quartz and plagioclase. But rock types like that are very low volume, and you're not in a common rock type. However, you can have quartz with both plagioclase and alkali feldspar. That's fine. And indeed, we've looked at a few examples of some, well, what are broadly speaking called granites, but you remember they're not actually granites. Rocks with quartz, alkali feldspar, and plagioclase feldspar. So that's perfectly okay. And we've just mentioned the fact that if you've got omphacite, you will have, you should at least have your garnet index mineral in there as well. So that will be a giveaway for that. Tourmaline, we mentioned tourmaline last week, that frequently occurs with either white mica or quartz or both together, so you get all three. So if you think you've got tourmaline and you've got mica and quartz there as well, then that's a good bet that you've identified your tourmaline appropriately. And remember, with things like plagioclase is a mineral that is more common, calcium rich particularly, more common in the mafic rocks. So basaltic composition, gabbros and things like that, you're likely to find plagioclase. Plagioclase is much less common in the more felsic rocks. So that's something to be aware of. Pyroxenes are more common in the mafic and ultramafic igneous rocks. You do get pyroxenes in granites, but they are not common, and there's not a large volume of pyroxene in granites, or so-called granites. Similarly, with the amphiboles, you can get, under some circumstances, you can get some amphibole within quartz-rich felsic rocks, but it's not common. But you will find in the intermediate rocks like the andesites and the diorites, things like that, you can find that you've got mica and amphibole in there as well. So the two will go along with that. So if you think, for example, you've got something in there and you think it's olivine, and you've also got something which you think is quartz, one of those IDs is likely to be incorrect. So you need to think again. So always have a good tour round your hand specimen and take in all the various bits and pieces that you've got. Remember, if you've only got one tiny little black speck, and that's the only tiny black speck, within a reasonable size specimen, ignore it, because it's it's just not representative. And remember, you can't always identify everything unequivocally. So associations are important. Right. Okay. So we look at our rock. There's a little sort of table that we run down, and we've got that first estimation. Oh, get this thing out of the way. We've got, does it have a crystal shape or is it granular? And if we've got a granular appearance, then we come down this side. So these are the granular sort of anhedral materials. And here, color can give us a very good ID for our mineral. For example, if it's colorless, it could very well be quartz, which we could confirm by this clear, glassy, like broken glass, for example, that very clear, glassy material. If it's colorless and it's clear and glassy, but it's also greasy, then it's likely to be nepheline. And again, we'd confirm that by other associated minerals that we think we've ID'd. If we've got a granular material that is an olive green color, then that's likely to be olivine. But remember, you can have gray olivine, so be aware of that. If we have a granular appearance, but it's a deep, bright green, then it could be omphacite. Remember, you'd use a garnet for corroboration of that ID. If you've got something which is either pink, red, or black and anhedral, then you're likely to be talking about garnet, particularly if it's got these nice glossy luster to it. And finally, if you've got something that looks like white spots, then it could very well be one of the felspathoids. So those are the anhedral rocks which we could run down an ID by just looking at color. Now we come over to the ones with reasonable crystal shape, and here we're basing our identification on the shape of these crystals. So you have to have some reasonable size. And remember, you need to look at everything you've got in your hand specimen, which is why I keep saying the bigger the hand specimen, the better, the more representative your minerals are. Because some of your minerals, particularly if they are more tending to be subhedral, you might have to hunt around before you can see a good example, before you can get an idea about what the crystal habit is really like. So if we've got these lath-shaped crystals, elongate lath-shaped crystals, then it's one of the feldspars, either plagioclase or alkali feldspar, and we can then use the other characteristics to identify further. If we've got prismatic crystals that are stumpy and dark, then pyroxenes are indicated there. And remember, you've got the cleavage indicators and so forth for that group of minerals. If the crystal habit is in the form of sheets or flecks or flakes, like we've mentioned here, then these are likely to be the micas of one sort or another. If we've got bladed, acicular, needle-shaped crystals, particularly if they are pale to deep blue, then, as we've seen just now, that's likely to be kyanite. But if our bladed acicular needles are, instead of being pale to deep blue, instead they are dark green to black, then that's amphibole. I've not mentioned it here, but if they happen to be that very deep indigo blue, then that's the amphibole glaucophane. That's another metamorphic mineral. And finally, if we look at our crystals and they are elongate prismatic and they are black, then that's an indicator for tourmaline. And we would then look at the other identification features of tourmaline to confirm that ID. So hopefully, having come to the end of this little series of talks on the identification of minerals, what you need to do now, and have a look through your own rock collections and just have a go at trying to identify what you think you've got in your rocks. And if you've got questions, then you can ask these at the next edition of the assembly. So that will give you an opportunity to look at that. So what I'll do now, I'll open this up to questions, and as I say, this is